For over a century, high-performance automotive design has centered on a single, uncompromising rule: weight is the enemy. Every extra pound makes a car slower to accelerate, harder to stop, and more difficult to throw into a corner. For decades, European legacy brands built their reputations on stripping mass away. They obsessed over forged aluminum and carbon fiber, creating low-slung, rigidly mechanical machines where lightness dictated speed. Then, BYD launched its ultra-luxury sub-brand, Yangwang, and introduced the U9. From the outside, it has the aggressive proportions of a traditional supercar, but under the skin, it weighs a massive 2,475 kilograms. That is nearly 3 tons of mass. To compound that weight penalty, engineers rejected the industry standard. Instead of using lightweight ternary lithium cells typical for high-performance vehicles, they installed an 80 kilowatt-hour lithium iron phosphate, or LFP, blade battery. LFP chemistry is heavy, but highly thermally stable for prolonged track use. By all the old laws of mechanical physics, a vehicle carrying that much bulk shouldn't be competitive. Yet, a version of this exact car recently shattered the 300-mile-per-hour barrier. The U9 didn't reach those speeds by conforming to traditional aerodynamic or weight-saving methods. It achieved them by using brute-force digital computing to turn its heaviest physical disadvantages into highly calibrated weapons. The first major engineering hurdle was straightforward. How do you violently accelerate a vehicle hauling 2.5 tons of metal and battery cells? This top-down schematic illustrates BYD's E4 platform. Instead of a heavy central engine, an independent motor sits directly at each wheel, enabling independent torque vectoring. As the vehicle enters a turn, the outer motors spin faster while inner wheels brake, forcing the chassis through. Together, those 4 independent motors generate 1,287 brake horsepower and 1,680 newton-meters of torque. That output propels the U9 from 0 to 62 miles per hour in 2.3 seconds. By entirely digitizing how power is delivered to individual contact patches on the road, the E4 architecture effectively renders traditional mass-based acceleration penalties obsolete in a straight line. Acceleration is one thing, but keeping a heavily weighted vehicle from flying on dusty asphalt during high-speed cornering presents a different problem entirely. Traditional coiled metal springs simply cannot manage that much lateral momentum. To solve this, the U9 uses the DICE-X system. This cross-section shows a kinetically driven hydraulic actuator replacing the traditional spring. When cornering, it lifts at 500 millimeters per second, instantly generating a ton of counterforce to keep the heavy body perfectly flat. When the U9 first appeared online, videos of the car jumping entirely off the ground from a standstill or driving smoothly on only 3 wheels went viral. These public stunts were direct